The goal of this video is to talk about wave reflections, and we're going to start kind of simple here and build this up. I want to emphasize that this is probably something that seems cheesy and easy and stupid, but you should actually pay attention to this because it rears its head several different times during this semester of coursework. So that's enough on motivating. So let's start by trying to visualize this. I've got what's called a free end here and a fixed end. So I've got a string and I'm just going to flick it and the wave pulse is going to travel here. Maybe this free end is somehow supported by magnets or something, but the idea is it can move up and down without having some significant tension on it right there. So this is free to move up and down. And then this one, it's tied to a rigid support. And so I want you to think about what's going to happen here when let's go to the simulation. When we run this, I think having the simulation on screen will help. Let's go to this one. All right. So what I'm going to do is I'm going to wave pull this, run this wave pulse, and I'll provide a link to this simulation in the comments. But so I've set this up. Notice the following. I have high tension in the string. I have no damping, so we have no friction to die. If I put damping on here, what does that mean? We see the pulse start to die out. So I'm going to do an ideal case. Obviously, in the real world, this is totally plausible, but I'm going to go to no damping so we can see this. Think to yourself, what's going to happen if I lower the tension? Ready? I decrease the pulse speed. So I'm going to go ahead and keep this up here at high and run this again. All right. So more tension, more wave speed. So now let's show you a loose end. So again, I want you to think about this, and I'm going to run this in slow motion. I'm going to pulse this thing, and I want you to think about what's going to happen as we step forwards here. I paused the simulation. How is this pulse going to be affected by that free end? Will it invert? Will it turn upside down or not? Take your guess. Taking your guess supposedly helps you remember the answer better. So here we go. We're going to step this forwards and see what happens. I'm just stepping it forwards. What happens to the wave pulse on the free end? Will it invert or not? The string pulls the free end way upwards. We see that there's interference. The pulse is now twice as high because the first half of the pulse has reflected and it's interfering with the second half of the pulse. So remember, the pulse was about like this. Well, pulse came in. There's another pulse coming out that's the same height. And when that basically causes it to double in height. Okay, so that's why it gets much taller. And then, whoops, let's keep stepping this out. Now it goes backwards, and we see the wave pulse does not invert. Let's restart that. Let's pulse this and watch it. It comes in, it goes way up, and it does not invert. Okay, so now let's see what happens with a fixed end. Let's restart this. Let's do the same exact thing, and I want you to think about this. As we get close, what should happen? That clamp is huge, right? It's not going anywhere, so think what should happen. The string pulls up on the clamp. By Newton's third law, the clamp pulls down on the string, and that's going to cause this pulse to momentarily disappear. Why? Let's think about it. There's one half of the pulse that's coming in. The other half of the pulse got inverted and it's going out. At wave superposition, this part of the wave combines with that part of the wave to give no wave. And now if we let this keep rolling, we see the pulse. Oh, whoops, the pulse is inverted. Whoa, this looks kind of cool. That was not my intent. Let's clear that all out. Like I said, let's do this. Let's do this and restart this one. So now let's watch what happens to one pulse and notice both ends are rigid boundaries. Okay, so it hits the fixed end, it gets inverted, it's headed back towards the first part, which is fixed, it gets inverted, And so we could see this happening over and over again. And then if I show this at normal speed, you get to see these cool patterns. We can get some weird patterns. Whoa. I'll leave the link to you and you can trip out on this and maybe, I guess I should have dropped acid. My bad. That wasn't in the prerequisites. Okay, where were we going? Oh, I'm stopping the share. There we are. We're going back to the book. Let's summarize what we saw out of all this. And then I actually have a physical demonstration to show you this, and I can show you a real example of a free end and fixed end here. All right, so in this case, the pulse reflects off a free end. We saw it is not inverted. Okay, the reflected pulse of a fixed end was inverted. Again, that seems like I'm spending a lot of time just to show you this. But you just got to trust me. This is going to show up multiple times, especially in optics. Okay, so now I've got an example of this. Hold on. All right, let me zoom out a little bit. Okay, so I've got this situation over here. We've seen this wave apparatus before. All right, and now we have this long section and we've got the short section. So I want you to think about this as this is sort of like a string with a large mass density because the rods are very long. There's a lot of mass per unit length. And this is like a string with a low mass density. The rods are short. There's a relatively small amount of mass per unit length. Now let me get this thing set up here. Actually, what I could do is just start with the big one. We'll uncouple these. I'll move this slightly. So these are not attached anymore. So now I can rotate this. And what's going to happen here is when I flick this, this wave is going to reflect off a free end, right? There's nothing holding this end down. So what I want you to do is I'm going to flick the pulse and I want you to watch what happens to the pulse when it gets here. Does it invert or not? And then I'm going to keep holding on to this end so you can see what happens to the pulse when it gets back to my hand. Whoops. Oh my God, that was sloppy. Let's try this again. Okay. Okay, doesn't invert. It's inverting. All right, so I know this is hard to see, but I'm trying to give you an example. So this is one example of a free end, and this would be me holding on to it would be a fixed end. So now I want to go to the next level, and I want to couple this, and I want you to take this one step further. I want you to imagine what should happen when we have a wave on a string that goes from high density to low density, or vice versa. Give me just a second. Very, very high-tech coupling mechanism. I'm coupling these two strings together. I'm joining them. Just some rubber bands here. So now I want you to think, what will happen to the wave when it hits this spot? Some of the wave will reflect and some of the wave will be transmitted. And I want you to think about what should happen both to the speed of the wave and to the reflection. Does it get inverted or not? And the transmitted wave, does it get inverted or not? Here we go. Okay, I saw something there. In particular, I started an upwards pulse here, right? And notice when the wave gets to here, this thing initially went up. Now let's try and see what happens to this rod as well as the wave gets reflected backwards. So again, I don't know if you can tell, but hopefully you saw that this wave did not get inverted and this wave did not get inverted. And you probably noticed the wave travels faster in the low density material. It definitely travels faster. Let's try this the other direction. And then I'll summarize on the whiteboard all this crap. So right now, just keep watching. So I'm going to pulse it. There you can see it a little bit better. Look at the transmitted pulse. It definitely starts with an up pulse, right? So I'm starting with an up. Gradually destroying this thing. Whoops. So again, I'm going to start with an up pulse. And notice the up pulse is transmitted, but try to look at the reflected pulse here. Notice the reflected pulse gets pulled down. All right, I think that's enough on this. Let's go summarize this on the whiteboard. Give me a second. I hope that looked cool on the screen. I really have no idea. Trying my best here. Ha! Those tennis balls. Not bad. All right. So in this case, what did we see when the wave started on the more dense and went to the less dense? We see this was effectively doing this, where we had the pulses did not invert. And then in this case, the reflected pulse got inverted and the transmitted pulse was not inverted. That's what I was trying to show you there. Okay. So, and now if both strings have the same tension, right? You can imagine if you're pulling these two strings taut, the tension in this string must equal the tension in that string. Otherwise, this interface would be moving left-right. But if we think that's true, V equals the square root of force of tension. Oops. All over the mass per unit length. And here's what I was saying. If we have the same tension, the less dense string has a smaller mu, the wave travels faster in that medium. All right, that's pretty good. Let's leave it at that.